administrators, welcome to today's Grade 11 Maths Show, proudly brought to you by Macmillan. Today we have a special revision lesson on trigonometry. We have selected highlights from lessons shown early in the term to help you revise and prepare for your June exams. You can download the notes for today's show from learnextra.co.za/live. Now it's time to get on with today's lesson. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision.
Let's look at some examples. Simplify the following expressions. Okay, so the first thing we need to look at is, and I'm going to work with A first. So I'm just going to rewrite A over here. So we've got cos squared of 180 minus beta, and we're dividing that by sine of 90 minus beta. And then I'm multiplying it by tan of 180 plus beta. Remember just now I said to you that you cannot do reduction formulae if we don't have the diagram that helps us to resolve which quadrant we're actually in. So always draw the Cartesian plane, 0, 90, 180, 360. I'm not going to fill this in, but fill in the quadrant where the angle will be. So 180 minus beta will be second, 180 plus beta will be third, and 360 minus beta will be fourth. Then, first thing we're going to look at is the cos of 180 minus beta. Now, I know that it says cos squared, but we're not going to deal with a square just now. We're just going to first deal with the ratio. So our starting point is the angle. Where is the angle 180 minus beta? We've rotated all the way with a terminal ray all the way to the second quadrant. So one thing we haven't put in is what ratios are happening. So all are positive, sine is positive, tan is positive, and cos is positive. So we've got what we call the Cos Rule. So in this second quadrant, we have that cos is negative because sine is positive. So we've got a negative cos beta, but now they said we need to square it. So brackets around that linear, and that's going to be squared, divided by. What is the sine of 90 minus beta? Remember with the theory, with the key concepts we looked at, that anything that adds up to 90, they are called cofunctions. So the ratio doesn't stay the same, but the ratio will change to its cofunction. I like to call that rule the Coco rule because the angles are complementary and the cofunction, you have to add that prefix to it. So I call it the Coco rule. Whereas with 180 minus, 180 plus, and 360 minus, the ratios remain unchanged. So sine of 90 minus, complement. So the complement is going to force me to create a cofunction. So I'm going to get the cofunction of beta. And then I'm multiplying it by, what do we look at first? The position of the angle. Which angle am I looking at? I'm looking at an angle that's rotated to a terminal ray in the third quadrant. The moment I'm in the third quadrant, the tan of that angle is going to be positive. So therefore that reduces to the tan of beta. So when we talk about reduction formulae, we're talking about a formula that will allow us to rewrite that ratio as a ratio of an acute angle where the ratios are actually the same. So for example, if I had tan 60 degrees, then if I add 180 to it, tan of 240 is also the same ratio. They're different sized angles, but that ratio is the same. And that's key to know, that we're working with the same ratio. So a reduction formulae, in essence, is just another way of writing a trig ratio, so that the ratios are the same size. And hence, we have these formulae that allow us to rewrite that complex angle as an acute angle. Once we've got that to that stage, then we can do some simplification, and we have that the cos can go into that cos, so we're left with a cos beta, and now we're multiplying it by tan. But a tan beta can be written as the quotient of sine over cos. Remember our quotient identity? It can be written as sine over cos, so we land up simplifying this as the same thing as sine beta. Okay, so reduction formulae is encouraging you to rewrite what appears to be a very complicated looking expression into something that can be rewritten as an acute angle. Now let's go up and see what we've got here. Right, now here's also something quite long, something quite complicated, and we're just going to rewrite it. Actually, we're not going to rewrite it, we're going to talk about it. Let's look at it in terms of this function. What about this new one? Now, when we looked at our quadrant over here, we saw that we had 180 minus, 180 plus, 360 minus. We did not have that. Cos x, cos 24, cos 90 minus x. I think we can do something like that, sine 66. We've got sine squared plus sine squared of 450 minus x. Okay, so that one does not look at all like any of the ones we've looked at. So there's a little bit of theory we need to discuss, and that is what happens with negative angles. Okay, and the theory about negative angles is that the sine of the additive inverse is the same as negative sine A, whereas the cos of negative A is the same as cos A, and the tan of negative A is the same as negative tan A. So if you change the angle to its additive inverse, you're changing the sign as well of the ratio. The only one that stays the same is the function that is symmetrical about the y-axis. And that function is the cos function. So cos, if you're drawing it there, you draw exactly the same thing on the side. It's a mirror image about the y-axis. And so you change the size of the angle, but the ratio stays the same. You change the angle, but the ratio stays the same. The ratio does not change. So this function, because it's symmetrical about the y-axis, change the sign of the angle, the ratio remains unchanged. Whereas with sine and tan, change the size of the angle, the additive inverse, that ratio will change. Okay, so that's what's very important about negative angles. So if we go back up, and we're trying to see, well, what is this tan of negative 180? And I can see that it's the same as the additive inverse of that angle. So we said that if you change the size of the angle, you change the sign of the ratio. So it becomes negative tan of 180 minus x, which is applying our negative angle rule. Cos x is already acute, I'm not going to do anything to it. Cos 24, we're not going to do anything to it. What about cos of 90 minus x? That becomes sine x. And sine of 66, I'm not going to do anything with it yet. What about sine squared of 450 minus x? Anything that's larger than 360 degrees, the terminal ray will be the same ray if you take away 360 degrees from that. So this one's going to be sine squared of 90 minus x. And now that we've got the cofunction, we can work with that cofunction, we can work with that reduction, and we can simplify that. Yes, we left off where we were trying to simplify a fraction that included reducing of a negative angle, and it included reducing of an angle larger than 360. So let's get back to where I left you. That was, we had already reduced, and we were sitting with these acute angles. Now, if we are to reduce to an acute angle, and they are already acute, then I'm not going to do anything with them until I've done some kind of simplifying around me to see what I'm left with. So I'm left with a tan of 180 minus x. So by the end of the session, you need to be able to spewing out which quadrant I'm in second quadrant. Tan is negative in the second quadrant, so I'm going to get a negative of a negative tan x. And then I've got this cos x multiplied by. Now I've become clever. What's 24 and 66? That adds up to 90. So these two are cofunctions. So if I change that to sine 66 or to that to cos 24, I'm going to be able to divide. Now you'll find that these questions, when you are to reduce to an acute angle, say do not use a calculator. That's just because we need to see how you would use expressions to be able to simplify without actually going to find the values on the calculator. So I'm going to change that to sine 66 already. And then I'm going to get that all over sine x, and that's going to be sine 66. Then I need to add on a sine squared x, and I have a 90 degree. 90 is a complement, so I'm going to use the Cos rule, complement, cofunction. So that becomes the cofunction, which is cos squared x. Then, from there onwards, how else can we simplify this? Well, I have tan can be written as a quotient. Remember, it's either quotient or the square function, square identity that I'm looking for. That I can write as a quotient of sine x over cos x, and I've got times cos x over sine x. This I can already divide, and I can see that's 1. And then I've got on here these two terms. And what do these two terms add up to? The sum of the squares of sine and cos will always give us 1. So I've got a plus 1. Simplifying this gives us 1 as well. So 1 plus 1 actually gives me 2. So that very complicated looking fraction actually reduced down to a value of 2, which means that whatever x is, doesn't matter. That fraction will always come down to a 2. Okay. Right, so let's see a little bit more of reduction in action. Very popular question. If cos 25 degrees, and you can go to your calculator, you can find out what t is. But it's saying if it is t, express the following in terms of t. That is a traditional question for reducing. So, because we're reducing, we're going to keep next to us all our little notes that we're going to have an angle in the second quadrant, we're going to have an angle in the third quadrant, we're going to have 360 minus, and we're going to have our quadrants. We're also going to, in the quadrants, have that everybody's positive, sine is positive, tan is positive, and cos is positive. So we're going to keep that information. We're also going to keep the information on the negative angles, that sine of negative A is sine A. We're going to have cos of negative A is cos A, and we're going to have the tan of negative A is negative tan A. So we're going to use some of that information, and we're also going to use the very popular Cos rule. So our Cos rule says that if I have a sine of 90 minus, then it's going to be the same as the cosine of A. So those two angles add up to 90. That doesn't look very well written. Let's just make this a little bit more legible. There we go. Right, so now we have cos 25 is t, express the following in terms of t. We can look at this in a very algebraic way, or we can look at it in a pictorial manner. I'm going to show you both ways, and then you can decide what you'd like to use. So if cos of 25 is equal to t, without a calculator, I could actually draw a triangle that has got a 25 degree in it. So how big is this angle here, if that's 25? Well, those are complementary. So that means this angle is 65. 65 and 25 is 90. And if cos of 25 is t, it means that my adjacent side, this side here, is t, and my hypotenuse is 1. So I could actually work out, that's my given information, I could actually work out this side over here, by using Pythagoras. So this side would be the square root of 1 minus, I don't know why my pen is not behaving itself today. Right, there we go. Square root of 1 minus t squared, just by using Pythagoras. So now I can define sine 25, tan 25, sine 65, tan 65. The moment I have an angle in a triangle, I can actually solve for the other three ratios. And I can solve for the three ratios of the angle that's complement to it. Okay, so a very powerful tool for you to be able to work with reduction formulae. So in this case, if I'm looking for the tan of 25, then tan of 25 would be opposite over adjacent, which would just be that. So my tan of 25 would be square root of 1 minus t squared over t. Okay. What about the sine of 25? Well, the sine of 25 is opposite over hypotenuse, so it would be that over 1. Now, I said to you I would show you an algebraic way of solving for this, and it would actually be something of this sort. We would want to ask ourselves, what is it that connects? What connects sine 25 and cos 25? How are these two connected to each other? The only way we can connect them is if we take their squares, then the sum of their squares will equal to 1. That's the only way I can connect them. So if they've told us that cos squared 25 is 1, then it's equal to t, then sine squared 25 is going to equal to 1 minus cos squared 25. And in that way, the cos of 25 is equal to the square root of 1 minus t squared. Now, if you remember from our diagram, cos, this should be sine, hey? This should be sine, so we've got the sine of 25. So if we go up here, on our diagram, we saw that sine of 25 was opposite over hypotenuse. So it's the square root of 1 minus t squared. So I've shown you a way of using the identity to find the unknown ratio. But for me, the most powerful tool is actually a diagram, because the diagram supports what you are thinking in the vacuum, which is really the identity stuff. Sine of 65 I don't really have to go into. It's the same thing as cos 25 as a cofunction, or it's t over 1, whichever way you'd like to look at it. What I am interested in is, how do we reduce sine of 245? So what is the sine? And this is question D. What is the sine of 245? Okay, we did not put down our theory notes for nothing. Okay, we're going to use that. And the first place where we start is the position of the terminal ray. Where is the terminal ray? 245, which quadrant? Quadrant 3. So we're going to be able to reduce sine 245 as the sine of 180 plus how many degrees? We're going to have to add 55 degrees onto that in order to get to, or how many degrees must we add onto 180 to get to 245? And we certainly must make these calculations really simple, and either use your brain or use the calculator, but try not to write those formulae all the time, because in your matric final you're not going to have enough time to write down what the formula should be and then coming back. So we should already be saying that it's 180 plus, and I would always encourage right, we would use your calculator. But for those of you who have not yet done reduction formulae, I'm just going to write down what the formula would be. So terminal array is quadrant 3. This is in quadrant 3, which means that I'm going to say 180 plus 65 degrees. And the reduction comes in saying that this third quadrant angle is the same ratio, gives us exactly the same ratio as negative sine 65. And why is that? Quadrant 3 has got tan as positive, so therefore sine of that angle will be negative, and so we'll get it that it's the same as sine 65. So I can't say that sine 245 is equal to sine 65, and test this on your calculators. Punch in sine of 245, what does it give me? Sine of 65, what does it give me? Every single ratio in quadrant 1 will be a positive ratio. So if I put in a negative, it means I am taking the additive inverse of that ratio, which is what I'm saying that sine of 245 equals to. So that would be negative sine 65. And I can now go back to my picture and say, well, sine 65 I've already got. It's t over 1. So therefore, this must be negative t. Okay.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, Remember to post on the page or send an email to helpdesk@learnextra.co.za. We have got such exciting news for you. From July, a new program starts on Mindset, just for you. It's called Connections. We'll chat about the issues that affect your life, your school, and your relationships. We'll have fun, take your calls, and have great prizes up for grabs. Connections, from the 1st of July, 7:30 in the evening, only on Mindset. For you, by you. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you on the page or on Twitter. Enough of the chat. Let's get back to revision.
Okay. The only thing about identities is you've got to be very good with your algebra. If you're not good with your algebra, you're going to struggle with your trig. Because whereas in grade 10, even grade 9, you worked with A's and B's and X's and Y's, you're now working with those very same terms, but they've just become trig terms. So instead of A, you're going to work with cos A. Instead of B, you're going to work with cos B. Instead of X, you're going to work with sine X, etc. So the whole algebra that you've learned, how do I add terms? How do I simplify? How do I divide? All those rules have to now be applied. So if you are poor in algebra, guess what? It's going to affect your trigonometry. Okay, so first one, A. We need to prove that this left is equal to the right. So the beauty about identities is they're giving you the answer. So you are getting an answer, and you need to work towards that answer. It's not like this empty vacuum where you don't know where you're going. They actually say, look, you need to get it to that. How are we going to get it there? Okay, we often work with a side that I can do something with. I can square, I can add fractions, I can simplify. So we work with that side. So there's a very technical way of doing this. You have to choose a side. So I'm going to choose my left-hand side. Okay, so the first question is to prove that sine x plus cos x squared is going to be equal to 1 plus 2 sine x cos x. Okay? And since I've chosen the left, you write LHS for left-hand side. And that is the same, or that's been given, not the same, it's been given as the square of that bracket. Now I'm not going to write the square. I'm going to say, what does it mean to square a bracket? It means I have two brackets that are being multiplied together, and they are the same. They look the same, they are the same. And how do I multiply them out? Well, I have a rule. You've all learned it. I FOIL it out, you often say. So let's FOIL it out. We get sine squared, and then we get the oil, the inners, and the outers. And can you see I get cos x sine x, and I get cos x sine x. So I get two of them. 2 cos x sine x. And then I do my lasts. So I get cos squared x. And then I look at it and I say, okay, on my right-hand side, I've got it. I've got that part. What about these two terms? What is sine squared x plus cos squared x? Square identity. It's equal to 1. So I can simplify and say, which is equal to 1 plus 2 sine x cos x. And then you say, which is the same thing as my right-hand side. So in other words, you have proved that if you write sine x plus cos x all squared, it is the same thing as saying that it's 1 plus 2 sine x cos x. So you have proved what we call an identity. Okay, let's just go back up there and see what the next one is. So take the left-hand side. Now, in B is a classic example of when you look at it and you say, well, I'm going to try and get all this into a tan x. Because it's a fraction, because there are terms in the numerator, because there are terms in the denominator, I'm going to simplify my left-hand side. So I would take my left-hand side, I would write it next door, I would say left-hand side, and as I'm looking at it, I'm already analyzing it. I'm saying, well, what could I do with my numerator? What could I do with my denominator? Sometimes you can't do anything with the numerator, so you go to the denominator and you see, I have two terms, and this cos x is in both terms. So do you remember factorizing the algebra? Being able to expand, being able to contract and bring things together again, being able to factorize. All those are tools for you to be able to do trigonometry. So in my left-hand side, I then sometimes start with what I can do, which is to take out the cos x, and then I'm left with the sine x plus 1. Now, this gives me a hint. If I have a sine x plus 1 in a bracket, then perhaps I would like my numerator to be in sine x. So my next question is, can I get the numerator into sine x? Is it possible? What is 1 minus cos squared x? And that's why now you have to be very well versed in the square identities. So I have to know that sine squared plus cos squared is 1, but you've got to know the ones that come through after that. 1 minus cos squared is sine, 1 minus sine squared is cos. Okay? And be careful that it's the squares. So it's got nothing to do with the linear. Sine x is not equal to 1 minus cos x, but sine squared is equal to 1 minus cos squared. So we now have that that's equal to sine squared x, and we've got this plus sine x. Oh, I'm sure some of you are jumping out of your seats at home to say, I can see, I can do something with my numerator. I have a common factor of sine x. So I can take out sine x, and what am I left with? A sine x plus 1 in my numerator over, no, we do not want to move that across, over sine x plus 1. Now I can divide. I can say that goes into that, and so I'm left with a sine x over a cos x. Remember our quotient identity? That tan is sine over cos, so we can now say that that's exactly the same thing as tan x. So identities are about algebra. I have to be able to factorize. I've got to be able to add terms. I've got to be able to expand, and I've got to use the rules of algebra always to help me. Okay, see a classic example. I need to add two fractions together. Two fractions that contain terms in the denominator. I need to be able to be good at adding fractions in order to be able to solve this problem, which is not really a solving, but it's a proving of an identity. So we've got 1 plus sine, 1 minus sine. Let's take it down times the cos squared. Let's see if we remember that. So we've got, okay, so this was C. We had 1 over 1 plus sine x plus 1 over 1 minus sine x, and then we're multiplying it by cos squared x. Right. First rule about multiplying fractions is that we find our common denominator. So it's 1 plus sine x multiplied by 1 minus sine x. This fraction has got that. It does not have that second factor, so it's got to be multiplied top and bottom by that factor. That fraction's got that denominator. It's missing that, so it's plus 1 plus sine x. And then everything is being multiplied by cos squared x. So we now get that minus sine plus sine is 0, and 1 over 1 is 2, and we get this 1 plus sine x multiplied by 1 minus sine x. Okay, and we're going to multiply it by cos squared x. Now you have a choice. There are quite a lot of choices here. It doesn't matter which one you take. It's not going to make anything longer or shorter. I would say that you need to be able to recognize that sine squared x plus cos squared x is the sum of two squares. So it doesn't have any factors. But the derivation of the subsequent identities that come out of that, the 1 minus cos squared and the 1 minus sine squared, they're actually a difference of squares.
Now it's time for a break, so don't go away. We'll be right back. Welcome back from the break. I know you can't wait for the term to end and the July holidays to start. And of course, that means winter school. This year, we will be repeating all the Term 2 Learn Extra live shows for you from the 24th till the 28th of June from 9 a.m. in the morning till 7 p.m. at night. So don't miss out. Go to our website www.mindset.co.za/learn/extra/winter school to get all the details and to download the notes for each lesson. But for now, let's get back to today's revision lesson. Over to you.
I've taken the liberty to use Macmillan's grade 11 textbook, Clever, Keeping Maths Simple, and just looking at two functions that have been drawn, sine 2x and cos of x plus 45. And they've given it to us in the domain negative 180 to 180. And just for better visibility, I'm going to sketch my sine 2x in blue. And I'm going to sketch, so that's F. And this graph here, I think it will look good if it is in yellow. So we're going to use a yellow. Okay. Let's just erase it a little bit here. And just fix it up there. Goes all the way up there. Okay. So they've actually labeled it for us. They've said that's definitely F, and G, that's the yellow graph there. The question is, write down the coordinates of the points A, B, C, and D. So A is this point over here. That's A. B is this point over here. C is that point there. And D is over here. Okay. Now, I'm not even going to look at the question. Okay, we've labeled it. We know we're looking at that. Let's engage with what has been given. Firstly, what kind of transformation is sine 2x from the parent graph sine x? What kind of transformation has that cos function undergone in terms of the parent graph? Okay. This one, what has been affected? The coefficient of x. This one, it's the term that's been added on. So what does the coefficient of x affect? The period. What does the coefficient, what does that constant term affect? The where you are starting with your maximum value of 1. So it will affect your starting value of 1. Okay, so engaging means let's go and work some things out. Okay, so let's work out, let's go down a little bit and do some calculations. Or actually, let's go on to another page. There we go. So they've given us the graph, and we're going to establish in a moment whether we agree with them. Y equals sine 2x. Okay. Let's see. What is the period of this new graph? The period is my period for my parent graph, and I'm going to divide it by the coefficient, which is 2. So that's 180 degrees. Okay, what do we do after 180 degrees? Is 180 degrees good enough information for me to be able to determine where the maxima and minima are? No. I need to find the critical values at which these x-intercepts and maxima and minima are happening. So I need to find the intervals. And the intervals, there are 4 of them I need to plot. So it's 180 divided by 4, which is 45 degrees. Okay? So now I can say that my graph is going to have 180 degrees, halfway, I've got these. So these values are 45 degrees, and I'm going to get a 0, a 1, a 0, negative 1, 0, where 45, because that's my interval that I've worked out, plus another 45, plus another 45, plus another 45. So this is saying start at 45, add another 45, 45, 45. So every 45 degrees you're going to be oscillating between 1 and negative 1. Okay, so we can go back in a moment and just see, are we happy with this? And then the other graph that they gave us was the graph of cos of x plus 45. Okay, we know that the cos graph has the y value of 1, 0, 1. Okay, 1, 0, negative 1, 0, 1. And the question is, when is this going to be 1? When is cos of x plus 45 1? When x is minus 45. So we're going to start at minus 45. No period change. The coefficient is 1. So I'm going to keep adding in 90s. So plus 90 would be 45. Plus 90 would be 135. Plus 90. would be 225, plus 90 would be 315. So we can go back and see whether we're happy that there is some intercept, some x-intercept happening at 45 and at 225. So we now can go back to the graph, because the graph was empty. They gave us nothing. They just said, here are the curves. We can go back and fill those values in. So don't be guided by the questions, rather be guided by the interpretation that you can extract from what was given. Right, so let's go back there. Okay, so we said the period of my blue graph had been changed. So that has to be a maximum at 45 degrees. It cannot be anywhere, nothing else except this has to be 45 degrees, because this was a maximum of 1. Then it went back to a 0 at 90. Then it goes to a minimum at 135. And then it goes back to 180. And it's doing the same thing on the side. So it would have a minimum at negative 45. It then goes to negative 90, negative 135, and negative 180. So now what's left is for us to say what's happening with the yellow graph. We should have really made it yellow. There we go. Okay. The yellow graph, we said its maximum has to happen at negative 45 degrees. So there's its maximum at negative 45 degrees. There's its maximum of 1, so we're happy with that. 90 degrees later at 45, it's going to have a 0. We're happy with that. And then 90 degrees later, and at 225, it's going to have the next 0, but the graph stops at 180. So we could work out what is happening at 180 degrees. How do we do that? If we wanted to know what y value was over here, we would take 180 plus the 45, and we would get what the cos value is of that. Okay. So now that we've established what is happening with the scale, it gives us a sense that we understand what is actually happening here. So the coordinates of point A, we've actually now worked it out without even going to find them specifically, but that would be minus 135, that would be minus 90, and that would be 135. What is happening at C is that we want to know at naught what is my value. So I'll substitute in 0, and I would get the cos of 45. So this value over here at C would be a y value of root 2 over 2. Okay. Interesting. What is the period of f? What is the period of the blue graph? So how many degrees does it take to get the function f? Well, how many degrees does it take? It starts repeating itself after that. So that's 180 degrees. Period is not a set. Period is one number, one value. Write down the period of G. What is the period of G? So how many degrees does it take to sketch the yellow graph? The period has not been affected. It's still 1x. So the period of the yellow graph is 360 degrees. The maximum value of sine 2x is 1, of course. And we'll end it off there. We hope that you had a good time with us.
Now it's time for a break, so don't go away. We'll be right back. Welcome back, Mindsetters. In case you missed my news, starting in July, we have a new program that is going to get you talking. What's on your mind? What are the issues you deal with? How can we help you? Connections will help you with all that and more, so make sure you catch it. For a fun and youthful look at life, connect with us on Connections. But right now, let's do some more revision.
Okay, so the question says, find the general solution for the equations and hence determine the x value in the given domain. Okay, doesn't matter what equation we're solving, we're always going to find the general solution before we work with any of the domains. So I'm going to leave out the first one because we've done enough of cos x. I want to look at B. I want to focus on what happens if you get 2 cos x is equal to negative 1 comma 456. Now notice I've solved 5 equations with you already, and I think you would have noticed that we gave you the equation in the form sine theta equals a ratio. So the ratio has to be isolated. Otherwise, the calculator cannot find your angle, because the calculator has only been programmed to find an angle when the ratio is by itself. So a note we've got to make to ourselves is that you need to isolate the ratio. So if the ratio has got a coefficient, I've got to say coefficient must be 1, because the calculator can only solve if the coefficient is 1. So I'm going to take that, I'm going to say 1, 456 divided by 2. Okay. Then my general solution I can now go and find. And what is my general solution? I'm going to take, firstly, I can see the ratio is negative. We've just looked at the cos function with a negative ratio, and we found that the calculator was programmed to give us an obtuse angle. It's very important that you predict what the calculator is going to give you, so that you can argue whether you're happy with that value or not. Maybe you've punched things incorrectly, and so maybe you don't totally agree with what's happening. So to go through the cos formulae, it will either give you an acute angle or it will give you an obtuse angle. And then the two other formulae will be the additive inverse of those angles. Okay? So if the cos ratio is negative, I'm expecting it to be an obtuse angle. Otherwise, we have done something wrong. Okay, so we can go fetch our calculator, and we can say my ratio is to find the cos of, and I've got a fraction, and I've got a negative 1.456, and I've got that over 2, and I've got that ratio. And notice how I haven't divided anything. I'm just putting everything into the calculator, because if I want to check later, I can see, have I got a negative? Have I got the right digits? Am I dividing by the right value? And that's equal to. Remember, we said we were expecting an obtuse angle. So it's 136,7. So that would be x from the calculator. X equals 136,7 degrees. And it says here, correct 1 decimal place. So that's why I've used 1 decimal place. And remember, it's period. That's one answer. We get a multiple set of answers. And from here, I don't really have to think about anything, because I can say straight away that my second set of solutions are going to come from the additive inverse plus K360. This only happens in cos, where it's the calculator angle and the additive inverse. Sine, we'll have to use a formula, 180 minus, and the tan, we don't have a second formula. So both sine and cos will always have 2, tan only has 1. Okay, so that's what happens. Now, when they say find find x in the given domain, we've now got to go back to this domain here and say, okay, I only want answers that fall within that range. So I want a solution set. That's what I call it. And the solution set would be, if k is 0, for example, then I would get x as 136,7, which is within the domain. I would get x equals negative 136,7. Okay? And if I then add plus 360 degrees, I would get 496. So that's too big. It's outside the 360 degrees. So if I minus 360 degrees from that, I get negative 223,3. And that would be okay. So x, if k was negative 1, then x would be negative 223,3 degrees. Okay? And if I then subtracted another 360 from that, I would get negative 583, which now you can see it's outside of that 360. So I keep adding on multiples until such time as it's not within the set. So I would actually get 3 values that affect that domain. Right, back to the trig now, grade 11s, and we left off with where we had the coefficient of the trig function was 2, and we had to isolate the trig function to make the coefficient 1, otherwise the calculator cannot find the angle. So now I'd like to look at something a little bit different. What happens if the coefficient is next to the angle? How are we going to treat that? Well, in this case, as long as the coefficient of the trig ratio is 1, the calculator can find the angle. But the calculator is going to find the angle 2x. So this 2 does not move anywhere. It gets attached to that variable that you are going to find the calculator angle, or 2x is equal to the additive inverse. So I'm just using too much space. I need to just space myself out a little bit here. So we're going to say 2x is equal to the general solution, or 2x is equal to the general solution. So when the coefficient of the trig ratio is 1, we can automatically go back and find out the angle that gives us 0.123. And that would be 82,9. So we've got 2x is equal to 82,9. Calculator angle, at the same time I've got to fill in the period. Or 2x equals, remember the cos function is symmetrical about the y-axis, so I need the angle that's symmetrical to 82, which is negative 82. I don't have to think about anything with the cos function. And I just fill in its period. Now that I've got 2x by itself, I can now solve for x. So I divide by 2 on the left, I divide by 2 on the right, so x equals to 41,45, so 41,5 degrees, plus 2 terms, I'm dividing by 2, so the period has now been affected as well. For those of you who've sketched the function cos 2x, will know that the 2 affects the period. But when you're solving for the equation, we don't have to think about how the period has been affected. The way that we are performing the algebra will bring out the new period. I don't have to go and write what the new period is, which is really nice. The algebra sorts that out for us. Okay? Or on this side, I'm going to divide by 2. I'm going to divide by 2. So x equals negative 41,5 degrees plus k 180. And remember grade 11, somewhere over here, I've got to say where k is an element that looks like a z, where k is an element of the integers. Otherwise, that's not true. Okay, so back to this one. Remember, when anything is happening to the angle, it stays there. And you will write your general solution in terms of the angle that you were working with. So it's 2x equals, and remember there's always 2 parts to it. Okay, so we dealt with what happens with the coefficient. We get rid of that. The angle, it stays. Now, let's go on to another slide. Okay, so this example, 2 cos x equals 0,87, we would have divided it by 2. The sine, what would happen there? Let's see if we can just extract this one there. Sine 2a is equal to 0,87. That's the equation, equals 0,87. And we don't really deal with a, so I'm just going to change that and make it an alpha. Let's make this an alpha. Angles come in Greek letters for some other reason. Okay, so I'm going to make that alpha. Okay. Can you see the ratio is by itself, so we don't have to isolate the ratio? And what is the formula for sine? The sine formula is 2 alpha equals my calculator angle plus its period. Or, how do we get the second? Oh, we haven't done this in a long time. How do we get the second value? It's always the 180 degrees minus the calculator angle plus K360. Grade 11, some of you around the country may use the reference angle. I use it as a calculator angle because that's where we find it. Doesn't matter, as long as you're referring to that one thing that is going to help you to find the general solution. So, let's go to our calculator. We're ready to find the ratio that gives us 0,87. So we've got, an angle of 60, 5. 60, 5. So 2 alpha is equal to 60, just check that again, 60, 5. 60, 5 plus K360. And now we can solve for alpha. So now you would divide by 2 and divide by 2 on the side. So alpha equals 30, 3 plus K180. And on the other side, we would have 2 alpha is equal to whatever that is, minus 180. Remember, working with the positive side there, so it would be 119, 5. Let's just get that. So it would be 119, 5 plus K360. We would now divide by 2 to just get to alpha. Divide by 2, divide by 2. So alpha would be 5, 9, 8 plus K 180. And somewhere we must write what's the nature of K, where K is an integer. So the general solution for sine is the calculated angle plus the period, or the second set of values is 180 minus the calculated angle plus K 360. Okay, so that's if the angle has got a coefficient. Okay, and then what about tan? This function over here, are we ready to solve? Yes, we are. We just have this complex angle in here, but that's fine. We're not going to worry about that. We want to go and find where is tan equal to negative 624. So let's see. Where is tan equal to negative 624? Where is it equal to that? At negative 89,9 degrees. Okay, so we would actually need to write down that it was the tan of, what did we have in the bracket? Theta over 2 plus 10. Theta over 2 plus 10 equals negative 624. Remember, the tan function is very friendly. It only needs one formula. So the angle theta over 2 plus 10 degrees will equal to negative 89, comma, do you remember what that was? 9. Negative 89, 9. And what is the period of a tan function? Excellent, 180 degrees. And one formula will give us all the tan solutions. We don't need a second formula. Tan is really, really friendly. So with that, I can now solve for theta, because theta over 2, I'm going to minus 10 this side. I'm going to minus 10 that side. So that's minus 99,9 plus K3 180. That's a variable. That's a number. So I'm only adding the numbers on numbers. And then what do I do to solve for theta? I multiply both sides by 2. So it's 2 times my negative 99,9 plus K180. And that gives us, if we just take on the calculator, that minus 10. And we multiply it by 2. We get negative 199.8. Negative 199,8. And 2 times that is K360. And that would be the general solution of theta, of that tan function.
We've come to the end of today's show. Thanks to Macmillan for making the show possible, and thank you for joining me and for participating in this revision session. Remember to join us for winter school from the 24th till the 27th of June, when we will be repeating all the Learn Extra live shows from Term 2. We will be back with live shows from the 15th of July for Term 3 lessons.